Hey everyone, welcome to C Prime. Hopefully you all had some time to grab some pizza. If not, got some over there. We've got a QR code for our C Prime talks. It's very important if you can scan it. Allows us to kind of get feedback, see how many people are coming to these things, and learn what we can do better, what we can improve on, what's going well. And so if you're new to C Prime is a organization. It's like a mentorship organization that does a lot of activities for inclusion. It also allows people to share their research experience and maybe along the way, inspire some undergrads or help people get excited. Right, and today we're gonna have Gracemarie. They'll be giving us a really interesting talk, so please enjoy.
Has everybody had enough time to grab the QR code? Cool. Okay, hold on. Well, it'll work as a laser pointer. Oh, wait. There we go. Okay. I'm going to be telling you about a thought experiment about gravity and quantum field theory. The title of my talk is An Elephant Behind the Moon. First thing we're going to talk about is, who am I? I did my undergrad at the University of Virginia. I was a member of the marching band. I also did undergraduate research in particle physics. It wasn't that productive. It says machine learning. I was supposed to do something related to machine learning. I didn't actually manage to produce anything. I was just rooting around in the computer system for a while, and my advisor was like, "Good job." The only other thing they had me do as an undergrad was there was a grad student who was developing this gluing process for these modules that were going to go to the LHC. And he thought he'd finished it. So then they said, "You, undergrad, you look like you're sufficiently bad at gluing. Go glue these things and see if the process works when you do it." I wasn't even there when they tested the module, so I don't even know if it worked. But I graduated with a BS in physics in 2022. And then I came here for grad school. I still do music. I'm part of the Grand Canonical Ensemble here on campus. My research is in quantum gravity and quantum information. I work with Oliver DeWolf here in the department. And I finished my master's exam in the fall. Too late to be awarded my degree in the fall, but I will be getting my master's in physics in May. I also have one more fun thing before we get to my research that I will talk your ears off about if you let me. This is my dog Milo. He is 2 years old and I just adopted him in December and I am completely obsessed with him. He is so cute. He is just the best dog ever. But we're gonna talk about my research, not about my dog, sadly. First thing we're going to talk about research is states and actions. Let's imagine that we have 3 tennis balls. Milo likes tennis balls. We have 3 tennis balls, and let's say we could paint either any of them green or red or blue. So the state that the tennis balls are in when we're done could be some sort of mix. We can also not paint the tennis ball, then it would stay yellow. So some possible states that we would get include this or this. We can think about it in terms of listing all of these states, or we can talk about just the actions. We can paint one of them green, or paint one of them red, or paint one of them blue. So now I would like you all to discuss with your neighbors how many states of these tennis balls there are and how many actions there are. Discuss.
Because it takes an action to create. Two actions. I think two actions. I think we count like different arrangements. Even if it's two different. You're saying number. So no, that's a good question. Because it said like paint one. Yeah. And then I just. Oh, I guess it's not. No, it's not. So it's if I say I'll take one grade of one sense. So there's only 4 actions. Oh, they talking about like unique action. Yeah. Oh, I misunderstood. So I guess yeah, if you interpret it any other way. That's kind of what I think. It may just mean. I don't understand. There's a lot of questions about it, so we're gonna. There's a joke where I spent it with
Okay, it seems like we've had a lot of discussion. I'd like to hear some feedback from the audience. What did everybody think about these two questions?
Does painting it or not painting it, sorry, does not painting it be playing, is that kind of an action?
Okay, so the question is, does not painting it count as an action? I would say yes, because usually when we count all of the actions, leaving something the same has to be one of them, just so that we make sure we've covered every possible action. We often call that like the identity, which means that it leaves the object alone. Does anybody have any further clarifying questions before we? Okay. What's up?
Does an action always act on one of the balls, or can I say like, I think one blue and one red, if that's one action? There's not two actions.
I would usually think of that as two actions that you've like combined, so you've done both of them, as long as they're on different balls. But that is a good question. Yeah, so the question was, are the balls able to be distinguished? Another way of putting this question is, if I had the state green, then yellow, is that different than having yellow, then green? I would usually say yes, because we're talking about tennis balls. But because we're going to later talk about small quantum things, you could also answer if the answer was no. Open to both sets of answers. Did anybody get any numbers? We don't have to have numbers. Okay. Okay, so what I'm hearing is 64 states. And actions, I think I heard 12. Okay, did anybody else get a slightly different number? Cool. I was mostly putting this up here to get y'all to talk about it. I didn't actually calculate the numbers. But if anyone's particularly interested in the answer in terms of numbers, we can talk about that afterwards. So now, as we were talking about with the distinguishable states and things like that, we're gonna add a dash of quantum in it. First thing we have to do when we do that is talk about a very foundational quantum mechanical experiment. So here we've got something to heat up a bunch of particles and send them through this very strange magnetic field. It separates them into two piles. These ones are spin up because they went up, and these ones are spin down because they went down. It just separates them based on their spin. This diagram shows that happening in one direction, so they're being separated in the direction the magnet is pointing. You can have the magnet pointed in a different direction. Does anyone have any questions about this? Cool. Now we have another discussion question. Let's imagine I had a series of these spin separators. I put in a bunch of random particles. I spin separate them in the Z direction, and I throw away the stuff that was spin down. Then I spin separate them in the X direction, and I again throw away the stuff that was spin down. When I put them back through the spin separator in the Z direction, what do I get out? Go ahead and discuss.
I can determine. I would be able to determine. Like, what's the election? I'd be like, it's going up. That was clearly going up. So like, you know, invariable theory is wrong. It's very over. You can see the invariant. I can see the invariant. You can see that makes sense. So you know with 100% accuracy before measuring. Yes. Right. You just go to. Yeah. Yeah. Thank you very much. How do you feel about what these are telling? Oh, it's.
Okay, we have discussed, we have eaten pizza, and we have discussed more. Does anyone feel like they have an answer or an intuition about what they might expect? Okay.
If I didn't already know how these worked, I would expect that I would only get the up because I was throwing away the down earlier and stuff.
Cool. Just for the recording, what was said was if we didn't already know some more quantum mechanics, you would expect to just get the up because you already threw away the down. One of the funky things about quantum mechanics is that you do not just get the up. You actually get both. This is very strange and a little bit unsettling. It took many people decades to feel at all comfortable with this sort of physical occurrence, but I gave you 5 minutes and I didn't tell you the answer beforehand. Hopefully that's okay, because we have to keep going. We're also going to talk about entanglement really quick. I tried to write a sentence about it and it turned out into a little poem. So I will give you a dramatic reading. Entanglement. Take two particles. If they are entangled right, no matter how far apart, when you measure one, you know the spin of the other. Thank you. The important thing to take from this is that entanglement means that there's some information sharing or some connection between things that can be physically separated. Finally, we're going to talk about a dash of quantum looking at space. How do we know if two places are next to each other? One of the quickest ways that I like to think about it is we look at how long it takes to get between them. So for example, when the second elevator broke, the bottom floor and the top floor of this tower got further apart, because on average, it takes longer to get from the bottom floor to the top floor. Entanglement, as we saw in the little poem, is also related to the flow of information, or the flow of things from one place to another, because you can know something about something very far away by only having done a local action. It turns out that different spots in space are all at least a little entangled with other spots. This means that my little chunk of the room over here is entangled with the place where the pizza's up. So something about my little chunk of the room is connected to the pizzas. Can anyone else tell that I'm hungry? Now we will finally get to talking about putting an elephant behind the moon. Yes.
Into a electron, and you were took half of them, let's say, and you then split, with the magnet thing. But then you split in the z direction, and you split in the y direction again, or the z direction. Because they're entangled with the electron you have, how could they be random?
Okay.
So,
I'll put this back up so that I can reiterate what I think your question was, and then we can talk about the answer. So what you're saying is if I had two bunches of electrons and they were entangled with each other, and I took one of them and I put them through this, would I still get the same result?
Yeah.
And would it have told me anything about the ones that I kept?
You measured the one that you kept. You knew that the one you kept was say spin down. Then with all, and let's say all the ones you kept were spin down. Would the end result of your experiment all be spin up, or would you still get a split? Spin up, spin down?
So if you entangle them such that their spins have to match, when I measure these and I get spin down, all the ones that I send through here would end up getting thrown out, and there'd be nothing in the rest of the experiment.
Okay.
If instead I entangle them so that they have to be opposite, so these are all spin down, I send the bunch through, they're all spin up. We've made a measurement and we've lost our entanglement. Entanglement can sometimes be thought of as a resource. So states on particles, when we entangle them, you can use up the entanglement. States on space, you can't use up the entanglement, because the space has to be entangled with the other bits, otherwise you can't say that it's still connected and still space. That's a subtle and interesting difference that you've managed to pull out here, which I think is very important. Are there any other questions before we move on to the elephant? Cool. I'm gonna rapidly flip through several slides so that I can get back to where we were. Elephant behind the moon. Just like we were saying with my chunk of space and the pizza, since the space is entangled, I can act over here, and that will act on the pizzas. So if I used a really fancy quantum computer or something like that, I don't know, I don't do experiments. I can just say that there's something that does that and I don't have to worry about it. And I did something over here, I could steal a pizza slice from over there. Or I could put an elephant on the moon by using all the possible actions on a chunk. I can do anything, anywhere. Now you might ask yourself, if this is true, why haven't I put an elephant on the moon? First of all, in practice, elephants and the things that set the scale of quantum effects are not similar in size. Elephants, in fact, are big, and quantum effects are typically small. This is sad, but also good for our sanity as human beings. Because imagine if all the elephants in all the zoos just disappeared and they showed up dead on the moon. I mean, they would asphyxiate anyway, so it's better if they're dead when they get there. That would be very sad for everyone. No one would be happy about that. Now talking more about, oh, what? I'm not sure the mammoths would be particularly happy about it, although I did see that apparently recently some scientists have mixed woolly mammoth DNA into some mice and made woolly mice. So instead of just comparing things that are big and small, if we talk about this in more detail, the action that I would do here that would seem to have created an elephant behind the moon would actually be a measurement on this entangled space of state. The entangled state of space. Mixed those two words up. And that measurement would only have a tiny, tiny probability of getting the outcome elephant. Unlike our unselected state that we sent through the spin select machine, where they should probably have equal probability. Elephant, very small probability. Reason, previous slide, elephant big, H bar small. The probability that I would have measured that I did create an elephant behind the moon also has the same odds as the quantum effect that would just poof, make an elephant on the moon without me doing any measuring. So I can't really be said to have created or put an elephant on the moon, sadly. I could observe that there is now an elephant on the moon, but I can't make it happen. Now, you might be asking yourself one very, very interesting question. Why was I thinking about this? What does this have to do with anything? The research that I do is about quantum gravity. That's a little strange because a full theory of quantum gravity is not yet known. We do, though, have some tools to learn about the properties we think it must have. And we use these properties to see what else we can learn about it. If it has any other interesting properties we can know about, that sort of stuff. This thought experiment illustrates the way that chunks of space have to be entangled and helps us dig into the details of how the actions on our chunk of space seem to affect other chunks while still preserving the idea that things cannot travel faster than the speed of light. This is the end of the science portion of my talk. I have a little day in the life calendar. So does anyone have any more questions about this portion? Okay. It's okay if you come up with some in the next couple minutes, because there is a question slide at the end. Ah, we have a question.
Very open. Seems like maybe space here is like very different from the way I think about it. And I'm kind of like trying to grasp like how it's different from the way I think about it. I guess maybe it has something to do with like actions, like actually creating actions, like containment itself, actually creating space. Can you maybe say something?
Okay, I think what I got, to restate the question for the recording, is an open-ended question about the way this picture of space and entanglement is different from the way we usually think about space.
Yeah.
Cool. One of the reasons that this is very different from how we think about space in our day-to-day life is because quantum gravity effects only come into play at extremely high energies or extremely strange situations. When we go about our day, generally, since h bar is small, we don't just have disappearing elephants. And that also means that the space that we see is something that we can move through, and we don't think of it as an active, dynamic participant in the processes that we're seeing and playing around with. If you want to start to think of space as more of an active participant in the scientific processes that are occurring, one good place to start thinking about that is looking at black holes. I can talk more about that later, but I think that gives a sense of at least why those two things are different. Any other questions?
Yeah, I'm also super not so familiar with quantum gravity. Is it, do you think that like the gravity is what's like entangling space or what's mediating that entanglement?
So the question for the recording is that as to whether gravity is what's entangling the space. That's a good question, because I didn't make clear sort of the direction those things go. It turns out that when we try to make gravity and quantum mechanics play nice with each other, we find that the space has to be entangled in this way. And so it's not necessarily that the gravity is making the space entangled, but it's that when you try to satisfy both gravity and quantum mechanics as theories, you get something where having the entanglement is the best solution. Any further questions? Cool. Day in the life. It's not actually a day, it's a week, because I do very different things throughout my week. And I had fun with PowerPoint transitions here, so hold on to your seat. This is a week. The first things that I think about when I'm structuring my week is my dog Milo. I get up and I eat breakfast and I walk him. And in the afternoon, I take him to the dog park and feed him dinner. The other things that I have that are very anchoring in my schedule include my teaching. I teach 2 different sets of classes. The little blocks are my office hours for the nuclear and particle physics class that I help out with. And the big block is when I teach lab in the basement. I also have marked out the times that I usually spend grading the homeworks or exams and the lab reports that people turn in. This is when my research group has our research meeting. And then the rest of the week, I mostly spend either commuting on the bus or doing research. But one important part of getting through grad school, or really just having a life at all, is making sure you have some time to have fun with friends. I include in here the times that I spend practicing my music, or going to trivia with my friends, working out, these kind of things. And then the open spaces, I usually spend doing chores or doing things that are my hobbies by myself, which include playing some video games, crocheting, knitting, those kind of things. Anybody got any questions?
How old is Milo?
How old is he? Milo is 2 years old. He had a couple of homes before I got him. The first one, he couldn't stay there because he kept chasing the cats. And then the second one, he was there for quite a while, and sadly his owner got lung cancer and couldn't take care of him anymore. So he went back to the shelter around Thanksgiving last year, and then I got him in the middle of December. He's actually pretty big. He's like 60 pounds. He's a big guy, but he's very calm and he is so soft. Does anyone have any other questions?
So is there like a rule that the more separated, like two segments of space are, maybe I'm thinking about that. But is there like a rule, like the more separated they are, the less likely that some observational computer can affect as well?
So when you have chunks of space that are more separated, those chunks of space are a little less entangled. The actions on one space have less likelihood of measuring something about the other space as they get further and further apart from each other. But like we saw with the in practice part about the elephant, you can't necessarily say that you are causing or affecting the other chunk of space, because the things that you seem to be creating there actually have the same probability of doing that even if you weren't making those measurements. Yes.
Or just like, if you like, shine it about infinity. Could any actions that I do now put something outside of that, like, or past that being played? Or is it only, so in other words, this entanglement travel past like?
So the question is about whether entanglement can travel faster than light or not. The entanglement can seem to travel faster than light. What it can't do is actually send information faster than light. So let's go back to thinking about those two spins. Let's say I had two spins that were entangled to match each other. And I gave you one and I kept the other one. You might make a measurement on one and get that it's spin up. That, if you're outside my light cone, you would know, if Gracemarie measures it, they're also going to get spin up. But I wouldn't know when to measure it or that you had gotten spin up until you had time to send me information that would have to travel at the speed of light or lower. And so while it can look like sometimes you can do a spooky action at a distance way faster than the speed of light, if you really sit down and think about it, one of the interesting things we've found in the last 100 years of physics is that it doesn't work like that. But if you do figure out how to send a message faster than the speed of light, let me know. I have a friend who works on patents that I met at the dog park, and so we might be able to get a good deal on that. Anybody else got any questions? Well, thank you.
Cool. Yeah, I guess there's a QR code at the end there.
Oh yeah, there is one more.
All right, yeah, I want to say that was an amazing talk. Like, I don't think I've seen that much physics covered in 50 minutes before, especially quantum physics. So it was very entertaining. Thank you, Gracemarie. Yes, we've got our QR code. So yes, please remember to fill that out. Leave us some feedback, comments, whatever else. And yeah, this is Sue Prime. We do these talks regularly, and we hope to see you again soon. And if there's any more pizza, anybody, feel free to grab some.
And a big round of applause for our host.
Cool, thank you, everyone.
I'll leave this up here for a little bit.
I get to pizza.